Pfizer is a pharmaceutical company that has relied solely on a patented hypertension drug for profits over the last 15 years. The company has an ongoing research and development, but it hasn't produced another successful drug because of the lack of motivation to invest heavily in R&D. With the patent on its only profitable drug set to expire in 5 years, and data showing that generic alternatives can reduce branded drug sales by about 75%, Pfizer now recognizes the urgent need to invest heavily in R&D. The company also believes that the increased investment will improve its chances of discovering a successful new drug. The head of the research and development team at Razer is responsible for selecting potential drug projects and assigning project directors. The department has decided to pursue 5 different drug projects. Namely, Project Up is an antidepressant drug that lessens mood swings, Project Stable, a drug for manic depression, Project Choice, a drug for a less intrusive birth control for women, Project Hope, vaccine for HIV prevention, and Project Release, a drug that is more effective in lowering blood pressure. Laser has 5 senior scientists, namely Dr. Kaval, Zuner, Tai, Mickey, and Rollins. To assign them to 5 new drug development projects, the company has implemented a motivation-based bidding system. Each scientist receives 1,000 bid points to distribute among the projects, with the higher bids indicating stronger preference.
Due to Taser's over-reliance on their hypertension drug, considering its patent expiration due in 5 years, the company now faces the urgent need to develop a new breakthrough product. But there are several problems that pose a threat to that process. First are scientist assignments. Taser must assign one senior scientist to each of the 5 proposed R&D projects. The challenge lies in making assignments that maximize total bid points or preferences, ensuring that each scientist is working on a project they are most passionate about to maintain high productivity and morale. Second, Dr. Rollins' potential departure. If she leaves, the company must abandon one project. The decision would involve sacrificing the project with the lowest overall bid support, ideally the one that scientists are least interested in leading, to minimize the negative impact on morale and output. Third, 4 scientists for 5 projects situation. If Dr. Rollins does leave, but Taser decides it cannot afford to drop any of the 5 projects, then one of the remaining scientists must take on a double workload. This creates a staffing dilemma where either Dr. Zuner or Dr. Mickey must be assigned to 2 projects, raising concerns over workload capacity, fairness, and whether this will still lead to an optimal distribution of preferences. And lastly, changes in scientist preferences. News of the possibility of some scientists taking on 2 projects has led to a shift in bid preferences, particularly from Dr. Zuner. This introduces new complexity into the decision-making process, as the company must evaluate its assignment strategy based on updated bids. It reflects the dynamic and unstable nature of team morale and requires Taser to remain adaptive in how it approaches project planning.
In the parameter dialog box, we set the objective to maximize the total bid points, which reflects the scientist's motivation for each project. The decision variables are binary, meaning each cell in the assignment matrix can be only 0 or 1, where 1 indicates that a specific scientist is assigned to a specific project. A key constraint is that each scientist can be only assigned to one project, and each project must be assigned to exactly one scientist. In cases where Dr. Rollins leaves, an additional constraint is added either to remove one project by setting its assignment sum to 0, or to allow one scientist, such as Dr. Zuner or Dr. Mickey, to be assigned to 2 projects. When preferences change due to internal news or morale shifts, the bid matrix is updated to reflect the new values before running Solver. All of these conditions ensure that the solution is optimal, fair, and aligned with Taser's goal of maintaining productivity and morale during critical time.
So now to present the formulas used and explain why we use this formula. We use sum to calculate the totals for each row and column. Then we use sum product to calculate the total preference points earned from all the assignments. In Solver, the objective is the cell that shows the total preference points. The changing cells are the assignments. Solver decides whether a doctor is assigned or not. We set constraints to make sure each doctor only works on the allowed number of projects and each project gets the exact number of doctors it needs. We chose the simplex LP solving method because it's best for linear problems that involve yes or no decisions. In short, Solver helps Excel find the best way to assign doctors to projects by maximizing preferences and meeting all the rules.
All right, right now I will be demonstrating to you how we built our spreadsheet model. So first things first, we need to set up the bid points table. Make sure to copy the proper variables and their values. For the assignment table, we mirrored the table. However, we will leave this blank as this will be our changing variable cells in using Solver. Now for supply constraint, all we do is to sum the rows, equal sign, and then we place the constraint here. We will only be assigning one doctor for one project, so the demand and the supply will be all one. And then for the demand constraint, we sum the columns. Now for the total preferences, we'll be using sum product. All you need to do is to highlight the light blue bid point table here and the yellow table here. Now for the solver, this is going to be what it looks like. So the set objective will be this orange table over here. The max, we'll be maximizing and our changing variable cells with this yellow table here. So our constraints will be binary. Make sure that the yellow table will only produce zeros and ones as this decision case, and we place our supply constraint and demand constraint. So make sure to align. So this is the demand constraint. Make sure to align the cell references, equal sign, and then the constraint will be the one in the light blue. Same with the supply. So make sure to check make unconstrained variables non-negative, and then the solving method will be simplex LP, and then just press solve. So this is our answer. As you can see, Dr. Caval will take a project stable, Dr. Zuner project choice, and so on and so forth. The one means that this doctor will take this project over here. And the total preferences is calculated over here. Okay, now for problem C, we'll be using the same table. However, we will need to change a bit of the constraints. So in this case, Dr. Rollins has left, so we can just black him out here. Make sure to change the sum product that it matches the light blue and the yellow table as well. And the constraints now is that Dr. Zuner and Dr. Mikey can either take 2. So we will be changing the constraint here. So Dr. Zuner less than or equal to 2, as well as for Dr. Mickey. However, we need to add another constraint down here saying that only either can take 2. So 2 plus 1 is equal to 3, or else this will become a problem in Solver where both of them will take 2 projects, and that's not the case for this problem. So we need to make sure that this constraint is added here to Solver. For problem D, this time it will be the same base model from problem C. However, Dr. Zuner has changed their bidding choices. So we already added here what's changed, and then all you have to do is to run the solver again. So everything else is the same, and you just press solve, and then here it tells us now which doctor will take what project. So all you need to do is to just change the values here, and it will tell us the most accurate answer. Now for problem F, you'll go back to the base model from problem A. However, we will need to change a bit of the table, but the constraints and solver is the same. So for example, Mickey cannot lead project stable and project hope, so it will be 0. Here in solver, it's just the same from problem A. And then just press solve, and then it will tell us the new combinations of doctors and what project they will lead. And this will be the total preference. Okay, now for the final problem, problem G, we are adding 2 doctors, and also we will be changing the constraint for project hope and project release, because we have decided that you need 2 doctors to lead. So we will be changing the demand here, and then we will be adding rows to Dr. Arriaga and the Dr. Santos. These are the new doctors that we have. So make sure to copy the values, make sure that the columns and the rows are correct to allot all the doctors, and also the sum product needs to match the bid points table and the yellow table. But the constraints will stay the same. Just make sure to also change the constraint for total assigned, since we've added 2 more doctors on the rows. But we just need to change a bit. And here are the assignments, and here are the total preferences. So thank you. All right, right now I will be demonstrating to you how we built our spreadsheet model.
To conclude, the core issue we address is an assignment problem, specifically on how to effectively allocate manpower, in its case with doctors and to various projects. For problem A, we have a table that assigns doctors to projects, achieving a total preference points of 2,551. And in problem B, the model determined that the project up would not be assigned by any doctor. For problems C and D, we have a summary table showing doctors to project assignment based on the criteria provided. In problem E, our answer is yes, as the assignments in the problem D are supported because the model is able to account the maximum preference and assignments. And for problem F, we also have a table that assigns doctors to projects. And for problem G, we have another table that assigns doctors to projects. Finally, in problem H, it is generally not wise to base decisions only on such an optimal solution. It doesn't maximize the total preference, and there can be a better solution for it, but it would require a more complicated model to solve the maximum allocated total preference. Our model focuses on individual doctor assignments and does not take into account team dynamics, which can be considered for real-world applications.
Thank you very much for listening.